All right. So today we're starting chapter 1. All right. 1 of 8. So you can look at it that way, chipping away. I did add that it's called Introduction to Data, chapter 1. Obviously, maybe not so obviously, but hopefully at the end of today, it'll be obvious that we will be talking about data all term, right? And so just in the broadest sense, statistics is the science of collecting, analyzing, and drawing conclusions from data. Okay? Today, we're just going to talk about just collecting data, but also establishing some key terms that we need for the rest of the terms. Right? And so at its very core, if I go back to our course outline from last day, then we said, okay, course content, blah, 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 and then bam, inference for categorical data versus inference for numerical data. So today we're going to introduce the difference between those two, introduce those terms, and then I want you to remember that it's very important that you know how to identify a categorical variable versus a numerical variable, because how you analyze them and how you talk about them is determined by what type of variable you have. Okay? And so, and it'll come back to haunt us earlier than that, but it's going to be very important in that kind of meat and potatoes section of the course, which I would consider the most important. Okay, so questions before I start my rambling. Okay. Let's pretend that we were to collect a classroom survey. Now, the only point of this is to just illustrate how we would collect data, what it would look like, how we would store it. But I think you have a pretty good idea of, okay, so we've got a series of questions, right? And just think about how you would organize this information. I think eventually, or pretty quickly, you'd arrive at a spreadsheet might be nice. Oh, what a surprise. Right? And so then think about how you would organize your spreadsheet, right? Most likely you would have each student that you've surveyed, right? Each student that's in your sample as a row, right? And then the results of each question in the columns. That's a pretty basic setup that you would probably arrive at on your own, right? And so we can ask things like, what's your gender? Well, it's kind of loaded, but are you an introvert or an extrovert? Also surprisingly loaded. But I'm both. I know. I am. I'm an extrovert with my friends, but an introvert just in general, I think. I don't know. I can't answer that. How many hours of sleep do you get at night on average? Hard to answer as well. All these are hard to answer, I guess. Except for the last one. So what time do you usually go to bed? How many countries have you visited? Might take some thinking. I don't know. And on a scale of 1 to 5, how much do you dread being here? Probably 0. What does that mean? That's not an option. I know, terrible, right? Because you don't dread it at all. You're happy to be here. We've got this imaginary information. Now, what we're going to do, like we established, we said, okay, probably organize it in a spreadsheet of some kind, and we're going to call that a data matrix. There's lots of different terms that we could use, but a data matrix sounds the coolest. So there you go. A matrix is just the way we organize information like this. And so here, this is usually a spreadsheet in a data matrix. So like we said, right, I would assign some number to a student. And so I've got observation 1, observation 2, all the way down to observation 86. What does that tell me? It tells me I observed information from 86 students. And so here, this I'm going to call, these are my observations, observation numbers. And we do that often because usually we have to anonymize the data, right? We don't care who was student number 3, right? We just care about, in the broad sense, how can we generalize to all students? And so then we just replace them with observation numbers. And we're not going to analyze the observation numbers. They're for us to be able to quickly look and see how many observations did I have. And then we can talk about observation 4, for example, but they don't communicate any information besides what I just said. So here we have 86 observations. Now I'm going to introduce some notation. All my fingertips are dead. That's not stats. It's just a fact. Some notation. We're going to use a lowercase n to denote the sample size. So a lowercase n is the sample size, or the number of observations, or number of observations. If you're reading research articles or basically anything where they've analyzed data, you will see a lowercase n somewhere along the way, right? And so it's good to be familiar with that. But in this case, n is 86. Right? I have information from 86 students. Yeah. So then, well, it's on here, so it's not that surprising, but the general name for all these categories is they're variables, okay? And so all of these guys are variables. Variables because the results vary, right, from one observation to the next, right? And so, and I noticed there's a typo here. It's extrovert, pretty sure, not extravert. That's something else, or nothing at all. I don't know. Anyways, doesn't matter. And so here, right, we've got these variables, which would be the columns in our spreadsheet. Notice that the observation number is not a variable because it's something that we've assigned to each row, right? We're not going to analyze it or anything. So here, oops, notice the observation number, oops, squeeze it in here, is not a variable. So it's not something that we would analyze because we don't care about it. Okay. So these variables, they are the things that we are going to analyze, right? And so in statistics, we analyze variables. I'll put variables in brackets, right? We'll start with 1 and then we build to 2 and we analyze more and more variables. But in general, we're going to be talking about just different variables. Yeah. Okay. Any questions about that so far? Good. All right. In terms of the types of variables that we have, right, any variable at its very core can be classified as either a numerical variable or a categorical variable. We've seen those terms, right? Chapter 6 and chapter 7. Right? And so you got to pick your path here. And for me in this course, this is where I'm going to stop, right? I don't care about the further classifications of continuous, discrete, or nominal, or ordinal. I'll change this, right? They exist, so it's good to know that they exist. But for us, our only classification is going to be whether it's numerical or categorical. Okay? The analyses stay the same, whether it's continuous or discrete. So obviously today I'm going to talk about the difference between the two. Although I think if you kind of think about just the words, you could probably get there on your own. Right? There's a lot of clues in the words that we use. If you had to guess the difference between a numerical and a categorical variable, for example, numerical, we're guessing, right? So could it be a number? Yes, it is. It is. It's any sort of measurement that you have made. Things like speed, weight, height, right? All those things are numerical. Okay. So let's talk about that first. So a numerical variable is any measurement. So that's good. So the clue's in the name, right? Numerical. Okay, is it a number? Yes, it is. And so things like speed, distance, height, all those things. In general, it's any sort of number, but I'm going to add another qualifier. Any sort of number that you might be interested in the average of. Okay? So if you want to talk about the average of something, right? The average speed makes sense. The average height makes sense to talk about, right? Those are all things that we would be interested in. Then I would call it a numerical variable. So here, you're going to ask yourself, does it make sense to talk about the average? If it does, then it's a numerical variable. You're going to treat it as a numerical variable. Today, and today only, I'm going to talk about continuous versus discrete. But then, like I said, we're going to zip it back up to just numerical, right? Any sort of measurement, any sort of number, right, is going to be numerical. Not quite, but sort of. Gets tricky, right? But any sort of number we're going to consider numerical. But what would be the difference between a continuous versus a discrete variable? Now, the reason I ignore these later is because it gets very, very picky. Okay, so a continuous variable is something that's on a continuous scale. So if you think about speed, for example, you've got a speed gun and you've got some speed, 43 kilometers per hour. Sure. What if you got a better speed gun? 43.7 kilometers per hour. That wouldn't make sense, but 43.3 kilometers per hour, right? What if you got a better speed gun? 43.31. What if you got a better speed gun, right? So it's continuous. It just depends on the thing that you're using to measure, but technically speed is on a continuous scale, right? And so then you've got this continuous variable. Now, what about age? Oh, dang, I think I'm 37 or 38. Honestly, for about 4 years, I told people I was 30. Started around 28. I was so excited to be 30, so I just kept saying 30. And then 29, I still said 30, and I was 30, and then it was 31, still said 30. 32, probably still said 30. So now I know that's not true because I'm far enough away from it, but who knows? I can't keep track. Anyways, 37. Am I exactly 37 years old? No, I'm 37 and 100 and some odd days and some hours and some minutes and some seconds, some nanoseconds, whatever, right? But that's not how we talk about age. So for that reason, I would consider it discrete. But you can see how it gets, you could talk yourself into it being continuous. Obviously, I'm not going from 37 to 38, although that's how we talk about age. So for that reason, I ignore it, right? It's something to think about, but as long as you recognize that, well, it doesn't matter. I want to talk about the average speed. I want to talk about the average age. They're both numerical, right? So categorical then. Okay, what about, I ask you, well, what's your hair color? That's not a number, right? And so that's fine. We can talk about hair color as a variable, right? Blonde, brunette. And we can have broad categories or we can have lots of little tiny categories, right? And so blonde, brunette, black, red, blue, whatever. And so, but all those response options are categories, right? And so that's why I like to use the term categorical, is because it prompts me in the direction of, okay, probably categories, right? And so here, it seems kind of redundant, but categorical is when the responses are categories. Responses are categories. Yeah. Things like hair color, hate to say eye color, but what's another one? If I ask you what year of school you're in, first year, second year, third year, fourth year, fifth year, victory lap, right? That gets tricky because, well, those are numbers, right? But do you want to talk about the average year of school people are in? Traditionally, no. Maybe it depends on what your analyses want to be about, or what you want them to be about. But usually we're interested in, this is how the first years felt, this is how the second years felt, this is how the third years are doing, blah, 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 right? And so then we would treat those as categories. Okay? So kind of a tricky thing, because you can't rely on, okay, I see a number, so it's numerical, right? And so you have to look at, okay, what does that number represent? Does it represent a category, right? And so here, year of school, right? First year, second year, third year. I guess first grade, second grade, third grade, whatever. But we're here in the college setting, so it makes more sense. Okay. So then my argument is, well, I don't want to talk about the average year of school. I would rather talk about the different categories and how they're behaving, right? And so therefore, I'm going to treat it as categorical. Now, this is the part that a lot of people don't like, in the beginning with stats is because it's very argumentative, right? And so as long as you use the right logic, right? If you tell me I am going to treat the year of school as a numerical variable, I'd say, okay. And as long as you say, because I would like to talk about the average year of school, okay, that's up to you, right? And so as long as you use the right argument, then there are more right answers, right? But as long as you use the right argument, I can't argue with that. Okay. And so the key is to know what argument to use, right? And then use it, right? Hopefully we kind of usually agree, but there are instances where I could be convinced either way, right? And there are test questions that I like to use because I want to see you use this argument, right? And I could be convinced either way, right? So it doesn't make sense to talk about the average. Yeah. Or would I rather talk about just the categories, the counts in each category, that kind of thing? Yeah. And categorical variables, I don't know why. So I stole these slides and I complain about them a lot, but they're still pretty good. But she has nominal or regular categorical data, which I would call nominal, so no natural ordering. No natural order. Whereas ordinal has natural ordering. Going back to hair color, there's no natural way to order those categories, right? There are ways that you could impose, right? By some color scale or alphabetically, right? Those would be different. Or maybe, well, maybe not. Anyways, so it doesn't matter. But year of school, first year, second year, third year, fourth year, has natural ordering, right? And so here I would say, as an example, would be hair color versus year of school has natural ordering. In terms of the analyses that we're going to be doing, we zip it back up. It doesn't matter if it's ordinal or nominal, right? It's categorical, okay? The only time that it matters is when we're presenting data. Then it really doesn't make sense to break the natural ordering, right? And so then you'd have to keep it in mind. But what I like to emphasize is, you know, all these things kind of intuitively, right? If you were presenting data, you wouldn't just go, oh, here's all my third years and here's all my first years and then my second years and my fourth years, right? That would feel wrong, right? So you wouldn't do that anyways. And so, but the reason is because you have this natural ordering, right, that you're going to use. If there's no natural order, then there are other ways that we can organize it, usually in some sort of descending or ascending order, right, from the data. Okay. The tricky part about statistics is that it's used in almost any field. So business, obviously, right? Anytime that you want to prove something, right? My product is significantly better than this other product. That sounds like a moneymaker, yeah? Well, that's stats. So you have to use statistics in a lot of different senses. Psychology uses stats, biology uses stats, everyone uses stats. And so every field likes to just tweak the terminology a little bit to make it extra confusing. And so here in this first chapter, I'm going to try to introduce you to kind of the multiple terms that could be used. Now, for me, I'm going to stick to numerical, and it's because it kind of nudges me, at least, in the right direction, right? It's a number, okay? But another term that we could use is for numerical, how do I do this here? Would be quantitative. So you could have quantitative data, and the reason I don't like it as much is because, one, it's hard to say, but also and spell quantitative, but also I have to take that extra step of, okay, quantity is an amount, which is a number, right? So the link is a little bit further out, still there, right? I love etymology, so kind of the roots of words and things like that, and so you can always kind of drill down into the word, and it will tell you what it is, right? And so here, quantitative is a quantity, right? But like I said, the link is a little bit further out, at least for me. Now, you are welcome to use quantitative and qualitative. I know what you mean. I'm okay. I'm flexible with these things, but I'm going to try very hard to just stick to numerical and categorical, because I know it's hard when you're first starting out. But if you've got some background in stats and you're stuck on these terms, I know what you mean. You can use them. That's fine. But categorical is qualitative. Quality has, so qualities can be put into categories. A little bit further of a stretch, I think, but they mean the same thing. Nice. So numerical, categorical, right? How we visualize these things depends on, do I have a numerical or a categorical variable? How I summarize these things depends on what type of variable I have, right? So it's going to be very important. So any questions before I move on to this unknown slide? It's going to be a surprise for me too. Boring. But I guess it's good to do some practice. Classifying these variables. So we've got this data matrix spreadsheet with how many variables? Let's start there. I've got 1, 2, 3, 4, 5 variables, right, in this case. So we're going to classify each variable, and I'm just going to copy pasta here just real quick. Okay, great. So here we have 1, 2, 3, 4, 5 variables, right? Because we don't count that observation number. That's just for us, right? As we're analyzing things, maybe we want to refer to some observation, but in general, we don't analyze the observation number. And so let's start with an easy one, right? Male, female, feels like categories to me, right? And so here, gender is going to be categorical. For maybe some practice, now it's not something that I expect of you, but if it's categorical, it can be either nominal or ordinal. And in this case, I would say nominal because there's no natural ordering. Just taking it a step further because I can. How about the sleep category? So the sleep was on average, how many hours of sleep do you get? And so 5, 7, 5.5, 7, 3.3. Now I'm immediately regretting going to the lower levels. Why? Well, I could be convinced, continuous or discrete, right? People are allowed to give me a very, very precise value. It's weird. How would you know? But I guess we've got sleep trackers and stuff. I don't know. But it's definitely numerical, right? I can be interested in the average number of sleeps that of sleep that people get on average. Gets weird because we're talking about the average of averages, which is something that we will be discussing, so it's good to get used to it. Let's say it's continuous / discrete. Like I said, I could be convinced. Continuous or discrete. Doesn't matter. The analyses are the same. Phew. I used to tutor psychology stats, or yeah, and so we have continuous and discrete, and they go like 7 layers down. They've got so many different types of layers, especially for categorical variables. Where is the distance between them the same, or and stuff like that? But we don't care about that. But just so you know, you can go even further. How about bedtime? Now, bedtime, right? I'm having to rely on what's given to me. So I have the data set, I know what the information looks like, and that's what I'm having to go to. Because if we talk about a bedtime, right, I could easily measure that time, which would make it numerical, right? And I could treat it as a number, right? And so, but then I look here and I see, oh, okay, it looks like there are bedtime ranges. And then I see why they're not getting very much sleep, because they're going to bed very late, very, very late, between 12 and 2, which I'm assuming is not noon, 10 to 12, 12 to 2, 12 to 2, 12 to 2, 12 to 2. So these look like categories to me, right? But I had to look at the data to see, to kind of guide me in the right direction. So here, this is going to be categorical. And this is from looking at the data. And here, so if I have a categorical variable, in this case, I do have natural ordering, right? I'd probably be in the 8 to 10 category, which isn't shown, but presumably it exists, right? And so 8 to 10, 10 to 12, 12 to 2, 2 to 4, no. But there is this natural ordering, right? And so I would call it ordinal. The number of countries visited. Okay. Well, I said number, so that's a pretty good clue, right? 13, 7, 1. Dun, dun, dun. I'm going to circle this so we can come back to it. Missing data. What a pickle. But in general, if we just ignore the missing data point for now, I would say that this is numerical, right? And discrete. Can you visit 1.5 countries? No. Or I'm going to say no. If you argue that you could, then sure, call it continuous, I guess. Just have to use the right argument. And so here it's numerical. Oops, numerical. And I would say it's definitely discrete, right? Because It's either 1 or 2 or 3 or whatever. We'll deal with this dread one, and then I want to talk about this missing value just briefly. So here's where we get to flex our muscles. I could be convinced either way. I'm leaning towards categorical. I know I had you at your edge of your seat. I'm leaning towards, which is it? What would my arguments be? If I wanted to argue that this dread variable, which was on a scale of 1 to 5, how much do you dread this course, right? And so, okay, it's going to be a number. I could talk about the average, right? If I'm interested in reporting on the average dread level of the class, then I would treat it as numerical. Now, for me, maybe I would be interested in, okay, how are these 5? So the level 5, okay, the highest on here is 4, so that's fine. How can I talk about and summarize those with a high level of dread for this course, right? For me, that would be interesting to see, right? But you can see how it's totally reasonable to want to talk about the average, and it's totally reasonable to want to talk about, okay, within these categories, how are people behaving, right? Which is how we use categorical variables typically. So this last one is a good example of I could be convinced either way, right? And so here, I'll move it up because I'll need more space. I'm going to say either, right? Numerical, right? If I'm interested in reporting the average, if I am interested in the average, and it's categorical, if I want to analyze those different dread groups, if I want to analyze the different, can I just call them dread groups? It's going to split across the slides, but you had to be there. So as long as you use the right argument, then I could be convinced either way. Questions about that one? Okay. So how about another pickle? What about a phone number? Just in general, a phone number. A phone number is a number, obviously, but would you want to take it to a client and say, all right, we found the average phone number is this. And they say, oh, that's nice. What are we supposed to do with that? Right. And so the average area code is, well, that doesn't make sense, because what would I prefer to have learned about? Oh, this is how people with a 250 area code feel. This is how people with a 778 area code feel. I think there's a new area code, 236. Is that a new one? Yeah. How do those newbies feel? The 236ers, right? 604s. Oh, geez. Right. And so, right, that's more interesting to me. Right. And so then I would say it's categorical. Right. And so here, since we don't care about the average area code, You could use it in reverse like I'm about to. I don't care about the average area code, therefore it's categorical. It is categorical, right? It would be more interesting because the average area code isn't interesting at all. So it would be more interesting to learn to summarize how each of the area codes feel or their responses. It would be more interesting to summarize by area code, which makes it categorical. So of course, A is out, B is out because they both have numerical, right, decoys. However, I'm still a little bit torn on, is it just plain categorical or is it ordinal? Numbers do have natural ordering, so I guess I could be convinced, but is there any reason to have 250 before 778, for example? Not particularly. So I don't love having the option between the two because I could go for either one. I know you guys don't like that. What? People always ask me because there are a couple of multiple choice questions on the tests because they're easier to mark. And so, yeah, but are there going to be multiple answers? No, there aren't. I make sure that there's only one proper answer. But in this case, right, we're just illustrating kind of the difficulties, right? And so here I guess there's natural ordering, so I would be leaning more towards ordinal, but I don't care. Categorical. And that's why I don't dig down any further than categorical or numerical. Okay. So there we had just individual variables. We were classifying variables. And later in the course, we're going to be talking about just relationships among variables. Now, we're not here, or I'm not going to talk too much about this scatter plot besides telling you that that's what this is. Okay, and so here, this is a scatter plot. A scatter plot shows the relationship between typically two numerical variables. Typically two numerical variables. Now, the reason I'm introducing this is because this is usually how we see things called a response variable and an explanatory variable. Okay? And so when we're analyzing things, broad strokes here, when we're analyzing data, then usually there's one variable that we're interested in, right? Things like GPA, right? How can I predict GPA? How can I figure out what kind of GPA, what do you need to do to get a high GPA, right? All those things. And so there's one variable of interest. And so the variable of interest, in a study is called the response variable. Now, the response variable is always going to go on the y-axis, right? So here, just as a refresher, this is your y and this is your x. Making, in this case, just from the graph, the response variable is on the y-axis. So then I can say, well, in this case, the GPA of the student is the response variable. It's the thing that I'm interested in. Okay. And additional terminology, we could use it, or we could call this the dependent variable. Dependent variable. Dependent. Oh man. Dependent. Not that you can see what I wrote, anyways. It's for me. Dependent. Thanks. Again, I'm just going to call it the response variable because for me, right, if I'm interested in this response, that makes more sense to me than talking about, okay, the dependent variable is the GPA. Well, dependent on what? Well, it's going to be dependent on the independent variable, but I'm going to call it the explanatory variable. Yeah. There's a couple of reasons I like that term better. One, because it has the x, which links it to the x-axis, right? But also because the explanatory variable explains changes in the response variable. Okay. And so the explanatory variable explains changes in the response variable. And so just to make a note here, could also be called the independent variable. For us, in this course, all our response variables will be numerical. Categorical responses, we can do that, but it's for a second course or potentially a third course. And so our response variables are going to be numerical, okay? Whereas our explanatory variables are typically numerical, right? Hours of study per week, right? Things like that. But we could have a categorical explanatory variable. So numerical or categorical. And I'll say numerical in this course. I don't want you to go out into the world and think that you can't do it. You can, but we're not going to get there. Yeah? And so, but numerical responses are the most common. And so in this case, right, we're trying to learn what the GPA is based off of the hours of study per week. Yeah? And ultimately, what are we trying to do? We're trying to predict the GPA from the number of hours that a student studies. And so here, right, later, what we're going to be doing is we're trying to we would like to predict the response from the explanatory variable, just in general. Right? So we want to predict the GPA using the number of hours that they studied per week. Oh my gosh. And no one stopped me? You didn't want to know about the missing data point? Oh. I was prompted by, can you spot anything unusual about any of these data points? Well, one thing that I'm looking at, okay, 70 hours a week of studying seems a bit rich. But also, definitely not possible is a GPA over 4. So then you'd want to go back and figure out, okay, is this a real data point? Probably not, because of how GPAs are constructed, but also probably a data entry error. And then you need to decide what you're going to do with that, right? Do you remove it? Do you try to change it? Ooh, tricky. Notice how I'm not telling you what to do. Oop. Lips sealed. I want to come back to this. Just mention it briefly because we will have missing. We won't in this class, but in life, there are obviously missing data points. So some things to consider here are, okay, is it missing? Whoops. What are the two obvious options? It's missing because they didn't answer, right? Does that mean that it has to be 0? No, right? Is it missing because it's 0, right? And so missing because it is 0, that's different from if it's missing because they just didn't answer, right? Then there is some number, right? 3, for example, right? That's not 0. That should be in there, but it's not, right? Or because they didn't answer. Either way, you still have to decide how to deal with that missing data point. Do you remove just this data point from just this variable, or is the whole observation gone? Right? That's something that you'd have to decide. And hate to tell you, it's one of those things where as long as you argue what decision you made, okay, that's fine. Right? I decided to remove this entire observation because of a missing data point. Usually what would happen then is you wouldn't have very much data left. That's a problem. So then you might say, okay, in order to preserve the rest of the data set, I'm just going to remove this data point from this country's variable. Right. So just things, so many things. So here we have another scatter plot. And scatter plots, we just said, are for looking at relationships between two variables. In fact, between a response and an explanatory variable. And so in this case, we have the head and the skull lengths of possums. It's cute. Only because I've read the textbook a lot, and there's this cute little picture of the possum. Anyways, so we've got this data set on the head and the skull lengths of these possums. And from reading this, there's no obvious choice for which one is the response and which one is the explanatory variable, right? And so the only reason that I know that the skull width is the response in this case is because it's on the y-axis, right? So sometimes that's the case. If I want to predict skull width, then I would put it on the y-axis. If I want to predict head length, I would swap it and put it on the y-axis, right? And so here, right, this is my y-axis, and so this is my, let's see if I can, my response, which means that head length is my explanatory variable. Okay. Let's see here. It's another one of those scenarios where I try to convince you that you already know all this terminology just intuitively, right? And so if I draw an arrow like this versus, I'll give you the other option like this, if I asked you which one's positive and which one's negative, I think that you would say for this one's probably positive and this one is probably negative. You'd be right, right? And so here, this one's positive because they're increasing together, right? As my X is increasing, my Y is also increasing. And so here, this is a positive relationship, whereas this is a negative relationship, which can happen, right? And not in this case, because it makes sense that as the head length increases, the skull width also increases, right? I can't even begin to imagine if the head length was increasing, the skull width is decreasing. You get this kind of weird looking possum pretty quickly, right? But that would be a negative relationship, right? And so if I had to summarize this relationship, right, I would say, well, it looks like a positive relationship to me, right? And because I can generalize, and we're talking broad strokes here, right? I see that there's some sort of relationship. They tend to increase together. And so I'm going to cut the no relationship because I feel like I could generalize this behavior. And so there is a relationship. And I would say that they're positively associated, right? Or related, I guess. We just decided that they're not negatively related. And also the reason, and I'm kind of picking up speed here because it's less important, but the word causes is what's really holding me back, okay? And so we can't talk about causation unless we have a completely controlled experiment, okay? And so we can't talk about causation. So notice causation is different from there's a relationship, there's an association, kind of wishy-washy words, but causation, so we can't talk about causation unless we have done, can I say have done a completely controlled experiment? Find data from a completely controlled experiment. But Emily, that'll never happen. I know, right? So we can never talk about causation is what I'm saying. From a completely controlled experiment. Okay. So that's important to keep in mind. So you're welcome to use things like there's a relationship, there's an association, but you never say anything about causation. Questions about that? So we can talk about, okay, are two things associated? Another word that we could use, so many words, right? But we could say that they're dependent, right? The skull width depends on the head length, reasonable, right? So same thing as saying that these two things are associated, there's a relationship here, right? And so, whereas if two variables are not associated, so there's no relationship here, right? Then we call them independent. Now, what would that look like, just briefly? Independent, so if we have some y and some x variable here, if they're completely independent of each other, then y doesn't care what x is doing, right? Well, what's that going to look like in terms of a scatter plot? Well, it's going to look like a cloud. Just a very low value of x can generate this huge range of y's. A very high value of x can generate the same large range of y's. So there's no relationship here. There's no nothing I can say about this. Another way, so here is just random scatter. So another way to think about it is if I asked you to draw a line of best fit here, where would that line go? Obviously, it would go like this. Well, no, I think it would obviously go like this. I think it would obviously go like this. Doesn't matter. There's no relationship, right? So when the line of best fit is not presenting itself, obviously, right, then there's no relationship. Okay. And you wouldn't talk about that. You wouldn't present something that has no relationship to your client, right? And so so then you move on to the next relationship that you want to investigate. So this is section 1.3 is on observational studies and sampling strategies. Now, this is where we're going to focus our attention because I've already said all I need to say about experiments, which are on the flip side of observational studies. So data is collected, from either observational studies or experiments. We're not going to touch on experiments. There are experiments that you could do in business, but it's so very uncommon that we're not going to talk about it in this course. And so for us, we're going to focus on observational studies, right? And experiments is section 1.4. But like I said, the only thing we need to know about experiments is it's the only way that we can establish causation, and only if I've controlled every little bit. Okay? So for us, we're going to talk about observational studies. How do we properly collect data from observational studies? And how I think about observational studies in general is you just sit back and relax and watch information come in, right? You've got your speed gun again, right? You're just observing how fast people are going. You're observing people's heights. You're observing their gender. You're not saying you're going to be 175 centimeters today. That doesn't make sense, right? You're going to be going this speed. Well, okay, speed limits, but right? We don't control anything. We just observe. Right? And so here we observe information. Right? How do you feel about parking on campus? Right? We just observe it. We don't manipulate it if we're doing things well. I want to potentially skip this one because I blab too much. Okay, fine, I won't. But just briefly, if we're collecting data, right, then there's always going to be some population that I'm interested in learning about, right? And we've already established that, okay, statistics is going to be when I take a sample from that population and then I use that sample to generalize it to the population again, right? What's one of the main things is that the sample has to be representative of the population, right? And so in order to be able to bring it back to the population, then of course my sample has to be representative of that population. And so one of these potential research questions are, can people become better, more efficient runners on their own just by running? And can people, so I'm going to say, all right, all people, that's the population that I'm interested in generalizing to. That's going to be difficult just in general, but here, that's the population we're aiming for. And so then we went out and we got a sample and our sample was a group of adult women who recently joined a running group. What did we do? Uh-oh. We went from all people and immediately just went to adult women. So adult women, that's 2 subcategories. And then another subcategory who recently joined a running group, right? That's a very specific subpopulation that's not representative of all people, right? And so that can be a problem, right? And so here, right, just think about these results. I can't generalize them to all people like I wanted to, but I am allowed to generalize potentially as broadly as adult women, right? Assuming that the data were randomly sampled from running groups, right? And even then, it's a bit of a stretch. I would like to have the additional thing, adult women who join running groups, maybe, right? But at the very best, we can generalize to adult women, okay? And so that's what you want to think about. So we've got these kind of lofty goals, but then ultimately, whatever we drew our sample from, that's what we can generalize to. You know? I am going to skip this slide because it's a lot of words, only to introduce the term anecdotal evidence, right? Anecdotal evidence is things like, well, my uncle smokes 3 packs a day and he's perfectly healthy, to, I guess, combat just the other data. And so, just introducing some terms here. It's always tempting, especially in the beginning. So if we're trying to learn about a population, immediately my first response would be, well, what if I could just sample the entire population, right? And sometimes it's possible, sometimes it's impossible, right? Thinking about ants of a certain species, even if I narrow it down to a certain species, I'm assuming there are different species of ants. No, I know there aren't. Right? And maybe even if I narrowed it down to in Kelowna, there's no way that I could take a census, which I'm assuming you've heard the term before. Census is when you collect the entire population, right? There's no way I can be certain that I've reached every single, what are those basic ants, those black ones, in Kelowna. There's no way. I couldn't, right? I can't take a census. And so, but I don't need to, right? And so that's the beauty of statistics, is we don't need to take a census. So initially we think, well, that's got to be the best thing to do, right? Take the entire population. But some problems are that it can be difficult to complete a census, right? Imagine all those ants. Did I do that one already? Did I do this one? Right? Even if you're just here in the courtyard, it'd be very difficult. Well, especially right now, there's hopefully no ants out. Right? But it's also very expensive, difficult and expensive. So, and expensive. So in terms of funding, you're not going to get it, right? And that's okay. That's why we have statistics. If we were able to just easily collect any population that we needed to, we wouldn't need statistics, right? Because statistics is when we take sample information and generalize to the population, right? But it eliminates the need to collect an entire population. Some other things, right? If you think about a population, even at this very moment, sure, right? The population is the same, or now it changed, probably just in Canada, right? And so it's constantly changing. And the beauty is that we can get very reliable results by sampling. So here, I want to have another page, but that's okay. we can find very reliable results from sampling, assuming the sample is representative of the population. Assuming the sample is representative of the population. The way to do that is by random sampling. Okay? And so we do this by random sampling. Ensures the sample is representative of the population. Now this one's interesting, but I am going to skip it, and I might skip the next one too. So the main idea here is that if you do random sampling, which is easier said than done, right, then you are allowed to assume that your sample is representative of the population, and that's a good thing. So of course, go back and read that. And go back and read this. Some problems standing in our way are things like you have your population, you've randomly selected from that population, you reach out and you try to get them to do a survey and they just will not do it, right? That's a problem because you tried to reach them and you can't get information from them. So that's called non-response bias. Okay. Bias is when the results are in a certain direction, right? So favoring a certain outcome. Voluntary response, right? You see a survey and you think, oh, I want to answer that, right? And versus a convenience sample, which is when you stand in the middle of the courtyard, or maybe in the e-building because it's terrible out, and you just survey everyone that passes by you. That's a convenient sample. It's convenient for you, but it's not a random sample. And so you can't generalize to the entire, even college population. The only way to do that is by randomly sampling. Right. A notorious example is the Literary Digest did a poll in 1936. So 1936, and they were able to reach 2.4 million people. They reached out to 10 million though. So a huge sample, but they tried to reach 10 million. It's ambitious, right? And so we've got a lot of non-response for starters. And what they found was that, okay, this candidate called Landon, who obviously didn't win, was going to be the overwhelming winner. And then FDR was only going to get 43% of the votes. And if you look at, okay, well, they got information from 2.4 million people. So it must be good, right? And so what happened was FDR won with 62% of the votes. And the problem was, well, they had huge non-response, but also when you go back and you look at who they had surveyed their own readers, right? Which, let me remind you, it was in 1936, and these folks managed to have a magazine subscription. Okay. Cars and a phone. Uh-oh. So now we've got this very biased sample, right? So there's no way that you could generalize to the entire population, and that's what happened, right? They said, well, we've got this sample, it's huge, so listen to us. And then it wasn't representative of typical voters at all. Right? Okay, so there are questions that I'm going to skip, but I'll put the answer in the notes before I post them. And so I encourage you to try it, but it's kind of a big read. And so we've already talked about observational studies. And I'm rushing because there's one thing that I want to talk about and then we're done. Prospective, retrospective. Again, the clues are in the names, right? Prospective is into the future, right? Whereas retrospective is looking back. They're just two different ways that we can talk about how we got the data. They're not terribly important, but it's good to know that you could be collecting future data or you could be analyzing past data. So one of the things that I keep harping on and will keep harping on is if you have a random sample, okay, you're allowed to assume that your observations are independent of each other. Okay. So here, random samples allow us to assume observations are independent of each other. Therefore, hopefully you guys are seeing the therefore shorthand, just 3 dots in a triangle. Therefore, if you haven't, now you have, and I'll use it. So therefore, the sample is representative of the population. Is representative of the population. Just squeeze it in there. So the most common sampling techniques, and there are many, but the most common are simple random sampling, okay, stratified sampling, and cluster sampling. So I just want to talk about these with my last 2 minutes, and then we're good. So a simple random sample is often abbreviated SRS. I mentioned that because a lot of questions will say you collected an SRS of size 45, right? That means that you can assume that your sample is representative of your population, right? Now, a simple random sample is you have your entire population and you randomly sample from within here. How could you randomly sample? There's lots of different ways. In this classroom, if I were to collect a random sample, I would go flip a coin. Anyone who got tails, you're in my sample. Anyone who didn't, you're out, right? Put names in a hat. These are all old school sampling ways. Names in a hat, I draw them, you're in my sample. What's a new school way? I work at the registrar's office, right? I've got a list of every student at the school. I put a number next to them or a student number, and then I use a random number generator to generate a list of random numbers, which I then attach to the list of students that I have. I can sort those, and I pick the first 20, 30, whatever, right? Those are a random sample of the population. There's lots of ways, but those are just kind of some key ways. Whereas a stratified sample is slightly more sophisticated. Okay, we've got strata, which are made up of similar observations. So they can be different sizes, the stratum can be different sizes. But what we do is we take a simple random sample, right, from each of the stratum, right? So we take a random sample of 3 observations from each of these similar groups. Then I put them all in a list, and that's my sample, right? Slightly more sophisticated. It's especially useful if I'm trying to make sure that I have representation from a smaller group, right? As opposed to cluster sampling. So clusters are usually not made up of homogeneous, which is just similar observations. So they're just kind of convenient clusters, right? Different classrooms, whatever. What we do in cluster sampling is you take a simple random sample of the clusters, and then you sample everyone in that cluster, right? And then that makes up your sample, right? So just slight variations, but those are the three main players for collecting data. But for us, simple random sampling is the way to go. There's a practice problem, experiments, but we already talked about experiments. Done. Step away from the plate.